If you are a Zcash user and you open your wallet recently, you may have experienced some issues and some major issues, such as your wallet not opening and not giving access to any of your coins. So whether it's a transparent wallet or it's a shielded one, there seems to be there are ongoing issues with the network. So today we are going to talk about the reason why these issues this is happening, and what kind of solutions what we can do. So there are things that it's out of our control, and unfortunately, these are things that have to be taken care by the developers of Zcash, and it needs to have some long-term solution. But before we get there, let's try to understand what's going on. So actually, the problem is twofold. There are issues due to the recent release of a network upgrade. So we're talking here about the Hello upgrade, and it activated, if I recall correctly, at the end of May, so about a month and a half ago. The NU5 in itself is a combination of several things. You have the biggest, most famous one is Hello 2, which is Hello 2 mentioned here, which is a new proving system that allows Zcash to remain shielded as shielded as before, but without the issue of the trusted setup. So with sapling, there was a ceremony, there was some data that had to be created, but that data had to be destroyed. It didn't really matter what value this data was, so it had to be random. And from that random value, we had to derive a bunch of other values, of a bunch of parameters. These parameters are now recorded in the file, the sapling parameters. But the key thing is that the origin of these parameters has to be destroyed. And failure to do so, if one person or one entity has this value, they would be able to create proofs without having to obey the rules of the statement. So if the statement says the sky is blue, for example, you could make a statement that says basically the sky is red, and the verifier would not be able to tell the difference. So obviously this is a major issue, major problem, and Halo 2 fixes that by offering a proving system that does not require a trusted setup. Unfortunately, it has other properties. It's not all roses. It's not all better. There are drawbacks. There are things that regressed. But all in all, at least from the point of view of the Zcash developers, having a non-trusted setup is more important than having a more efficient but trusted setup. That being said, this is not the real reason why we have this issue today. With the NU5, there was also a change in the transaction format. So if you go to the protocol paper, with the release of NU5, there is also a change in the transaction format, and this applies to all the transactions that are marked version 5. So transactions version 5 do not have to be including Hello 2 transactions or Hello 2 components. Hello 2 components are co-authored. So far you can see it here in a transaction, You can have transparent components, you can have sprout components, sapling, and finally orchard. So 4 types of components. In v4, so the previous version of the transaction format, you could have transparent, sprout, and sapling. Obviously, orchard was not available yet, so there was no way to have orchard components in the transaction. Right now, what you have is in v5, you have transparent, sapling, and orchard. So sprout is the one that has been dropped. So the oldest one is has been removed. And sprout, sapling, and orchard are 3 different ways to do shielded transactions. So that's the main difference, though, is that as you can see, even the transparent component of transaction v5 is different now than transaction v4. So the end result is that now in the network, you would have some transactions of v4, some transactions of v5, and they are not compatible. So if you have a tool, you have a wallet that understands v4, it would not be able to understand v5 without an upgrade. And a wallet that understands v5 it has to be compatible with v4. It's upward compatible. So a wallet that understands v5 will understand v4. So unless you have upgraded your wallet and your block explorer and your exchange, everything that has to deal with transaction, to if you have upgraded to support v5, then if you haven't, you would not be able to understand the transactions that are going on right now because of the NU5 network upgrade. So essentially you have what looks like a hard fork. So technically it's not a hard fork. I would say it's a hard fork, but I'm sure that some people will argue, in the sense that there were elements of the block. There are elements of transactions, so which are elements of the block that used to be invalid, that used to be rejected, but are now acceptable. So these v5, obviously, if you use a tool that does not understand v5, it would reject the v5 transaction. But now they're accepted. So whenever you have a change in the consensus rules, such as something that used to be rejected is now accepted, this is considered hard fork. If you have something the opposite way, if you have something that used to be accepted, but after the upgrade is rejected, so basically you're tightening the rules, then you have a soft fork. The problem with a hard fork is that if you have a tool, if you haven't upgraded the tool, it will not continue to understand the protocol. And this is what's happening in many of the cases right now. Many of the tools, all the old wallets that were not that didn't work with the ECC or didn't work with the Zcash team to upgrade, or all tools where the developer is no longer maintaining the tool, or block explorer that is third party and is not really actively maintained, have the issue that suddenly they stop working. They see these transaction v5 and they don't expect them and they don't know what to do with them. And because the format is such that you need to understand how the transaction is formed in order to not only parse it, but you also need it to understand the format, at least to skip over it. And right now, the v5 is a mystery, and these tools will suddenly stop working. So this unfortunately also affects transparent transactions. So even if you have a wallet that has nothing to do with Zcash shielded, so you're using, for example, a hardware wallet. And a good example of this problem is actually Ledger, the hardware Ledger wallet, and to some extent also the Trezor, suddenly stopped working So immediately after MU5, they stopped working. And I think that currently there are still issues with Ledger. And they are much harder to update than software wallet, because you have to push a change to the firmware. So that's one part of the issues that have been happening. But that's not the only problem. So this is already pretty serious, I would say. There are many tools that are not working anymore. So out of like 100, I think I would say like only like 5 or 6 tools work right now. So most of the block explorers do not work properly. Most of the wallets do not work either. But eventually this will be solved. The second issue, which is affecting shielded wallets, is somewhat even more serious. It's more serious because it's not something that can be just solved by upgrading the software. So the issue is can be understood pretty easily because there's the issue can be understood by just looking at this graph here. If you Google for if you look at this chart, you can see this is a chart that shows the block size as a function of time, and you can see that before the last couple of months, so for most of the duration of existence of Zcash, except some short peaks, the size has been really small. Right? We are looking at the unit here is bytes. So at most is like 50K to 121. But right now we're looking at nearly all the blocks have 1 megabyte. The maximum is 2 megabytes. So the blocks are not completely full, but I think that it's roughly 1 block full out of 2, because this is an average actually. So this increase of size of blocks occupancy, so the block has a maximum capacity of 2 megabytes, but before all the blocks were mostly empty, and this affects shielded wallets quite a lot. So to understand that, we need to understand how these wallets function. When you have you have seen in the past or many other blockchains getting to capacity. So this is not the first time that has happened in other coins. For example, if you look at Ethereum, when there was a surge in demand for Ethereum because of DeFi, blocks were getting full, and the fees were getting higher and higher. But besides the delay in getting a transaction through, so when you make a transaction or you make a call to DeFi, when the blocks were full, you had to wait a bit longer or much longer unless you wanted to pay a higher fee. So you just had to be patient, and eventually your transaction will go through. But the problem with Zcash is more serious, in the sense that it does not only affect the person that sends the transaction, but it also affects everybody who has a wallet and that has shielded coins. So why? The reason is that when you have a shielded coin, where is Zcash or Monero or any other coin, the transactions are encrypted, or at least hidden in some way. Therefore, if you have a coin, if you have an address, so if you have a wallet, you have a secret key, you will need to decrypt your transaction, or in this case, in the case of Zcash, you need to decrypt the notes that you have received. And in order to know that the note is yours, you need to decrypt it. So there's no particular identifier on the note that tells tells you that the note is yours, because having such an identifier would completely defeat the purpose of having a shielded coin. It would obviously identify the note to everybody and allow people to link transactions together. So this is impossible. This is by design impossible to do, and your wallet has to try to decrypt every note that's out there in the blockchain in order to find out the ones that it has received. And after that, it has to keep track of the evolution of these nodes. But the sheer amount of blocks that we have, in particular, these blocks are not only full, but they are full of shielded transactions. And these transactions are mostly spam. They are not transactions that are legitimate, because these transactions are extremely suspicious. They have very low amount of inputs, but very large amount of outputs. A typical transaction, or normal transaction that you would do, will have, let's say, 2 inputs and 2 outputs. We're talking about a transaction that has 1 input and 1,000 outputs. So this balance clearly indicates that the transaction is abnormal. But even though transaction is abnormal, from the point of view of the network, it is well formed. It is per consensus rules. Therefore, it could be mined, and currently miners are putting them into blocks. So as a result, these 1,000 outputs per one transaction, but we have many of them, have all to be trial decrypted. And this operation is not cheap. At the end of the day, if you have a wallet that has several shielded addresses, then the process of trial decrypting has to be repeated for every one of these addresses. And this also multiplies the work required by your wallet in order to process the incoming data. So one of the issues that we have, right, is, as we see, the blockchain has greatly increased in size because of the spam, increased in a way that is non-prunable. There's nothing that the wallet can do, the software can do, in order to eliminate the work. This work has to be done. Right? For a transparent coin, if someone spams, even somebody decides to make the same thing and create a ton of transactions that have a large number of outputs, it will actually not impact a wallet significantly. Because the output is identifiable, what would happen is that a server or node, even a node, Zcash day in that sense, will be able to index, would be able to identify which nodes belong to the attacker and which nodes belong to you. Right? So when you come and you ask for your nodes, your transactions, you can pass your transparent address, and the server will be able to directly identify that these nodes are yours, and then return directly the subset of these thousands or millions of nodes that are essentially decoys. They're essentially garbage. So for non-shielded public coin, this kind of attack is pretty much useless. But for Zcash, which is shielded and has a fixed fee per transaction, it's extremely effective. For a fee so we still have to pay the fee for the miner, but the attacker can easily make a transaction that only pays the minimal mining fee, which is 0.01 millisec, which is essentially free. If you do the calculation and with the optimal block allocation and transaction management, the attacker could create fully occupied blocks for as little as 6 cents a day, or about 6 cents a day, which is ideal case for the attacker. But even if you take a more conservative approach, it would be about $1 a day. So that's extremely cheap, because at this point the wallets are basically most of the wallets are basically down. They can't handle that much load. And this is also related to a second point I wanted to say, is that the wallets that have been created, so I'm talking about the Zec wallet or Nighthawk or Edge or these wallets, they have followed a pattern, design pattern that kind of mimics the pattern of a normal wallet, a wallet for a non-private coin. In particular, they have the notion of a multiple shielded address under the same account. So in Zec Wallet Lite, you create a wallet by a seed. You get a seed, which is our 24 words. But then in your wallet, you're free to create as many shielded addresses as you want. You just have to tap a button, and the wallet will give you another fresh shielded address. The problem with that is that this shielded address is actually not related to the other shielded address, besides the fact that they come from the same seed. So in terms of secret key, the secret key are different. And for the wallet to synchronize, all these shielded addresses will have to be processed separately. So if you have 1,000 nodes and 10 shielded addresses, even though they belong to the same wallet, these 10 shielded addresses will lead to 10 decryption per output node, which means that in that case you have to do 10,000 decryption, trial decryption. And again, most of these decryptions are fruitless. They would not give the node that you received, because this is a result of spam. These 1,000 addresses are not yours, right? But the wallet cannot assume that they are not yours, and it has to test. So it has to attempt to decrypt all these 1,000 nodes for your 10 different addresses. And again, this is the pattern of the shielded wallet that should have been avoided. There are properties, there are features of Zcash that are much better suited for these kind of scenarios. I'm talking about diversified addresses here. And they are much more efficient, since all these addresses are generated under the same secret key would be non-linkable, because there's a power of there are encryption, there are cryptography involved here. So basically, from the same secret key, you will be able to create as many shielded addresses as you want, but the decryption would be under the same key. So therefore, you will only have to try to decrypt one, and any of these addresses would match, even though all these addresses, from the point of view of an outsider, are different and non-linkable. So you have a combination of basically the worst of both worlds. You have wallets that have been designed to work with transparent coins, that now are faced with a surge of outputs that they have to decrypt, and users have not been informed or educated in the proper usage of Zcash coin, the Zcash accounts. And in a sense, they have been told that it's perfectly fine to create shielded addresses. So I've heard of people who actually have wallets that have more than 100 different shielded addresses. That's, in my opinion, I cannot see any usage, any reason, justifiable reason why you would need so many addresses. And the only reason why this happens is because the users have tried to follow the guidelines that are applicable to public coins. Because for a public coin, you would want to create another address for every transaction, because the transaction is public, and because failure to do so will allow any chain link analysis tool to follow your transaction pattern. So by habit, people have started to create new addresses whenever they need to make a transaction. But this is not needed. This is not required with a shielded coin. This is, and certainly not required with Zcash. In the past, there was no consequences. There was no problem with doing so because essentially there was no transactions going on there. So even if you had 100 addresses and 100 secret keys to try, you would not spend too much time because there were only like 1 or 2 outputs out there per block. So still have plenty of time. But suddenly these 1 or 2 outputs became 1,000 or 2,000, and the search is now 1,000 times more. So that's one thing, right? The second thing is that as a result of this, the wallets that have been designed to work with basically a very low minimum load on the system are now faced with a much higher demand, much higher load. And there are several things that they were using as optimizations that are no longer feasible. So if you take a fairly popular wallet, Zcash Wallet Lite, in order to speed up synchronization, they have designed an algorithm called BlazeSync. But BlazeSync caches the blockchain. And that means that it works, BlazeSync synchronizes the blockchain backwards. It looks for your most recent nodes from the end, and then rollbacks to the rows back in time. And the idea here is that it does so that your wallet seems to be available as soon as possible. And the assumption is that you open your wallet because you want to do a transaction and because you have probably received some money recently. So these heuristics make sense. But unfortunately, the blockchain has to be processed from forward in time. And as a result, the BlazeSync has to store in memory the entire blockchain or read it twice. So the blockchain now is suddenly super large. It used to be a few megabytes, and now we are talking about megabytes per block. So these megabytes per block is technically not the size that the Zcash Wallet Lite receives. We have a server in between called Lite Wallet D, which essentially prunes the blocks. So if you take a block that has, so if you take this block, for example, right, and it has a sapling, it has transparent, sapling, and orchard. So let's discard orchard for the moment because the attack is mostly using sapling transactions. So the transaction would have a transparent components and would have sapling components. The Lite wallet totally ignores the transparent parts. So anything that is transparent, or these elements, will be just discarded by the Lite wallet, because the Lite wallet purpose is to serve shielded transactions, the shielded parts of the transaction. So it is only interested in this part, right? The sapling components. And the sapling components have two sides. We have the inputs and we have the outputs. The inputs are called spans, and the outputs are called outputs. So the spans and the outputs are further trimmed down. So you don't have the entire sapling span and you don't have the entire sapling output. So let's take a look at what we have. So this is a span, and we have 32. These are the sizes in bytes of one sapling span. So if you spend something in your transaction, you're gonna get one block like this. Right? If you're basically spending one node. But this is not what the light wallet really needs. It will only take the nullifier. So all the rest, so we are 32, 32, 32, 32, 192, and 64. So all the other elements here, CV, anchor, RK, ZK proof, and span author signature, are not going to be transferred to the wallet. The reason why the wallet doesn't need that is because it assumes it's been connecting to a node that has done validation already. So it assumes that all this stuff is already valid. All it cares about then in that case is a nullifier in order to detect whether that particular span corresponds to one node that it owns. So for span, you can see now that that's a massive save in size. So from roughly, let's say 300 bytes, we went down to 32. So a factor of 10 to 1. Now for the output, we also have a big cut because we don't need all of this. We only need a CMU, ephemeral key, and the beginning of the ciphertext. So I think for the ciphertext, we don't need the 580 because this includes the memo. We only need I think about 60 bytes. So we need 130 out of this roughly 700, roughly 1K. So also a really big saving in size. So even if the block is full at 1 megabyte, I would say that the wallet receives, let's say, a tenth of that, so 100K. But at the end of the day, it's still a lot of traffic that goes through. So if you synchronize like something that is completely full, and we have a rate of roughly 1 gigabyte per day, we're talking about 100 megabyte of data that the Light wallet, your Zeg wallet Lite, or I'm taking Zeg wallet Lite as an example because it is the most popular wallet out there. So Zeg wallet Lite would have to download 100 megabyte per day of data if though the blocks are full. So that's one component. The download size is already fairly significant. If you are using cellular data, or if you're using roughly slow internet, you're not on broadband, 100 megabyte a day is not something to trifle with. So that's one factor. The second factor is obviously that if the wallet algorithm needs to store all this block data in memory before processing it, we get to a point where eventually, whether it's today or in a year, in 2 years, the amount of memory that is required for your wallet is going to be too high for the hardware. It's simple math. The blockchain increases in size all the time. There is nothing that can prune the blockchain. Therefore, the blockchain will never diminish in size. And if your algorithm needs to cache to keep the entire blockchain in memory, then eventually you're gonna have an issue, a memory issue. So that's the second problem with the current wallets. The third problem is how they do the trial decryption. So on one side you have, for example, 5,000 nodes that you don't know if they are yours or not, and you have 10 keys. So you have to try every one of these nodes with every one of your keys. So the combination is 5,000 multiplied by 10. So, and for each of these combinations, you're gonna have a result. So the trivial way to do it is to do one after the other, right? But a much more efficient way to do this is to use multiple CPU cores, because every one of these decryption is fully parallelizable. There is no common data between. There's no interaction, correlation between these data. So having solved one issue, in other words, there's no dependency between these calculations. And this is a type of calculation that can easily be done in parallel. So unfortunately, some wallets do not do that. They still do all the calculations, all the trial decryptions in sequentially. So that's one thing that also matters. And now the last part that really also extremely time consuming is the maintenance of a piece of data. It's called witness data. And this piece of data has to be updated every time you receive a note. So this piece of data is really specific to Zcash and to this to its proving system. The note that you own, whenever you want to spend it, you have to prove your ownership by producing a series of values. We call it a Merkle path, which indicates that you know the actual identity of that node, and it's yours. And in order to produce this path, so imagine this is a path through the forest, right? In order to you have, let's say, imagine you have a forest, and you have one tree is yours, and every node that comes somehow modifies the forest. So some other tree is planted somewhere. And what you need to keep track is the path between your tree to the exit. And knowing that whenever there's a new node, your path may change. It may not change if the tree is planted in other places, but you don't necessarily know easily if your tree path have changed. Therefore, the brute force, the way to do the calculation in a simplest way, is to update your path whenever there's a new tree coming. And you can imagine now that the problem is incredibly difficult, because you yourself could have fairly large number of nodes. You could have easily 50 nodes, 100 nodes. And now for each of the new node that arrives, so the node that arrives represent the changes in the forest, you are required to figure out if your path have changed. And to be fair, your path has changed in some way. So the path is multiple segments. So not all the segments would have changed, but we know for a fact that some segments will change. Therefore, we cannot just say, okay, we don't do the update. So we have to update, that's for sure. And we have to update based on every single node that we receive. So when the spammer created 50,000 nodes, he basically created a workload for all the wallets to update their witnesses, their path, for every one of their nodes. And with failure to do so, will make your wallet unusable. So your wallet has two factors. It has the ability to figure out which node it has received and which node it has spent. This is the part of the trial decryption. But there's also a part where you want to have the nodes and you want to spend them. So the second part is this Merkle tree updates. And you can imagine that the Merkle tree updates is actually much more compute intensive than the first one, or it could be much more compute intensive than the first one. It's debatable. It depends on the context. But both of these put together creates a situation where suddenly the surge of outputs, of nodes, of shielded outputs that the blockchain contains is now going to create a massive amount of work for all the wallets that are out there. And the worst is that this block, if you want, this work is not going away. It's in the blockchain. So you could change the rules. You could say that, okay, well, let's make some change that makes creating these kind of transactions too expensive or in any way prohibitive for the attacker, so that we don't have this situation in the future. But the past but the present or the past is already written. These transactions are already in the blockchain. So if you are unlucky and at one day, you need to re-import your wallet, and your wallet was created, let's say, a month ago, it will have to scan this part, because this part is here. We can change the future, we can make this, prevent this from happening, but these large transactions have already happened, and everybody would have to pay the price for handling them from now on. Okay, so this, all in all, these are the reasons why currently the wallets are struggling. So we have a problem where inherently the work is much harder. There's much more transactions, much more outputs, and this creates a much higher workload. Because we're talking about Zcash, the workload is even higher than if it was Bitcoin, and even if it was Monero. You pay some. The math is much harder. The compute is much harder. Then we have the fact that the wallets themselves were not designed to accommodate this workload. So they were making assumptions on the blockchain that are currently not valid. So the size is too large. So they cannot hold the blockchain in memory anymore, and they just crash. And third, the usage patterns that some people have, creating wallets with a lot of fielded addresses, makes the situation even worse. So all the three together means that some people are lucky, some people are able to synchronize their wallets because maybe they kept it up to date, and therefore the synchronization is only a few blocks, right? And maybe also they don't have so many addresses, or they have very powerful hardware. So all of these three factors would help them keep up to date. But for the large number of people who are occasionally synchronizing their wallet, and maybe synchronizing them like once a month, once in a while, and they have a lot of shielded addresses, they are essentially stuck. This is not going to work anymore. I've heard people waiting several days, and the wallet making no progress. It's like wallet like making no progress. So what can you do, right? So there's a wallet that I've written myself called Y Wallet, and from the day I designed that wallet, I had in the back of my mind the fact that these issues could come one day. So, in speaking of memory, the memory usage of Y Wallet, which is my wallet, is constant. And I make sure that the wallet synchronizes forward in time. So you not have a situation where the wallet is the blockchain becomes too large. Regardless of this size here, Y Wallet will adapt, and maybe in this phase here, it will be able to process a large range of blocks at the same time. But when it sees that you have a surge, and then you suddenly have a lot of outputs, it will just be able to process maybe a few blocks at a time. So this is basically it adapts its workload based on the number of outputs that you have, in order to keep the memory usage constant. The other thing is that it's streaming. So when it downloads a series of blocks, and then once it has enough work to do, to try to decrypt and to maintain the witnesses, it will pass this data to these components, these processors, internal processors, and keep downloading ahead a series of blocks, so that when the processing of the first chunk is finished, we have already data to work on. So there is a pipeline. If you're familiar with the concept, you have a pipeline where we try to keep the stages occupied by fetching the data in advance. And this contributes to some performance, but the main point is that we are able, Y wallet is able to work in a streaming fashion, and the blocks are been fed into the downstream stages. When they reach the end of the pipeline, they're discarded. We don't need more memory than the full pipeline. So this allows you to basically scale on very low-end hardware. Obviously, it would take much longer if you have low-end hardware, but I do test the wallet on fairly old hardware. So I use a phone from 2016, from 6 years ago now. Yeah, the phone takes like an hour to synchronize, but it manages to synchronize the entire blockchain from the beginning. So we have that aspect. The second aspect is that the trial decryption and the node management, everything is done in parallel. So there are some aspects you cannot do in parallel, but it's fairly minimal. And we managed to do the calculation of the witnesses and the trial decryption on all the CPUs that you have. And the number of CPUs is also detected at runtime. So if your phone has 2 cores, then we use 2 cores, 2 threads. If your phone has 4 cores, we use 4 threads, and the whole thing will automatically adjust, basically based on your hardware capabilities. So we have that, and I think that these two together allows Y wallet to basically synchronize the currently work when all the other wallets are failing to some extent. And again, if you have another wallet and you want to continue using it, you probably can, but it will take you some work. For example, if you have Zcash Wallet Lite and you want to make it work, you have to artificially create. You have to create a smaller blockchain. So you have to deploy another Zcash D, and then deploy like Wallet D, and somehow make like the Wallet D only serve a few blocks at a time, so that you basically spoon feed Zcash Wallet Lite with just a small amount of blocks. Otherwise, you would get overwhelmed. But that's not something you have to do with Y wallet. Y wallet would take care of that because of the streaming fashion, the streaming processing, and because of the adaptive memory usage and CPU usage. And finally, in Y wallet, we have an algorithm called warp sync, which also updates the witnesses. So the witnesses are as a reminder, are the path that are through the forest, which have to be updated whenever there's a new output, regardless of whether the output is yours or not. And this path has to be updated for every one of the nodes that are not spent. So we have an algorithm called warp sync that allows us to update all these paths at once, and this allows us to scale regardless of but the impact of having 10 nodes or 100 nodes is fairly minimal. It's pretty much logarithmic. So if you have it's actually even better than logarithmic. If you have 100 nodes and you have 10 nodes, it may be like 5% slower when you have 100 nodes than when you have 10 nodes. And that, with the batching and the grouping of the calculation together, allows us to do the maintenance of the calculation of these witnesses usually much faster actually than decrypting the nodes. So in traditional wallets, the trial decryption is fairly fast, maybe represents like 10% of the time. 90% is the witness management. With WarpSync, we are shifting the balance to maybe like 90% is trial decryption and 10% is witness maintenance. And also our trial decryption is faster than the normal one because we use batch trial decryption, which is there's some cryptographic advantage to that, and we also use multi-processing. All right, so before I turn this whole thing into an advertisement for wallet, let me finish here. If you have problems, you can give it a try. If you have problems with the wallet Lite or the other wallets, you can give it a try. But in any case, I hope that this discussion was interesting in order to understand why some may even say that Zcash is broken right now, that things are not working. Of course, it's a matter of opinion, but I do think that this is an indication that there are scalability issues with the protocol, and saying that the Zcash is able to process fast payment in a shielded manner is inaccurate at least at this moment. All right. I hope it was interesting. I hope it was fun to some sense. In any case, that's all I have for you today. And I wish you what day are we? We are Wednesday. Okay. Wish you a good end of the week. Cheers.